have to listen for so long is I'll break it up into two. So still today, but at least you can quick little lesson, try some questions, and then finish the lesson. So what I'm going to do with you guys is I'm just going to do multiplying first, and then give you some questions to try, okay? And then 10-15 minutes of practicing multiplying, then like I said, I'll come back and do division with you guys, okay? All right, so we've already done adding and subtracting functions, yes? Easy peasy, lemon squeezy. All right, so again, going to do multiplying first, let you do some practice, then come back and do division. So notation for multiplying functions, okay? So there's two notations to look for that means the same thing. So if you guys see these two notations, okay, they mean the same thing. So if you have the f and g inside the function, okay, together like that, with an x on the outside, that means you're taking f function and timesing it by the g function, okay. One other one that I have seen that we're going to add here, okay, is, do you guys agree that you're used to that closed circle dot meaning multiplication? So this, very rarely do they use this one with an actual dot, because technically, guys, do they need the dot between the f and g? You don't, okay? But sometimes they put a closed dot between the f and g. Tomorrow you're going to see an open dot between the f and g, which means something completely different. But I don't want to talk about that yet. I'm going to just stick with multiplying today. So this one, important, if you see this notation, it has to be a closed, blacked out dot for it to be multiplication as well. The first two are more the two that you will see. That means take those two functions, whatever they are, and multiply them together. Okay? So like this right here. Right? So do you guys agree that if you've seen this on an assignment or a quiz or a test, that that's very clear telling you to multiply? Right? So it's just saying take your f function and times it by your g function. So I'm just going to, you know me, I'm going to be very detailed on everything I write. So that highlighted piece right there means we are going to find our new h function. So to find our h function, right, so our h function equals, we're going to take our f function and times it by our g function. Obviously, you would not have to write that step, right? The highlighted piece is telling us to do that. So you can go right to step number 2, right? And do the substitutions. So what I mean by substitutions, this right here is your f function. It's going to get replaced right there. Those two things get replaced. Your g function is 3x minus 4. It's going to go in right there. Right, so you're just doing substituting, putting the functions in, then we're going to multiply them. All right, so our h function is our f function, which is an x plus 2 all squared times, and the reason why I'm using a solid circle there, do you guys agree if I put an actual time symbol that gets confusing? Because we're already using x, right? So the dot has its place in here when we have variables all over the place. Okay, so dot means multiplication, and then times my g function, which is 3x minus 4. Now, technically, guys, could have I just left the dot out of there and just put the brackets? Would that have been the same thing as well? Yes, because that would have shown multiplication too. So with that, technically that is our new h function, but if you have a degree less than a degree 3, you would be expected to expand it. Okay? So if there was a degree 5 somewhere, I don't expect you to go to a binomial times itself 5 times. And even here, guys, realistically, okay, you just, if you left it here because you can't simplify on a quiz, I would probably mark it right. Okay? But just realize on a quiz, and this was a multiple choice, or on a unit test, if this was a multiple choice, do you think your multiple choice would look like that? No, it would be expanded out. So let's just practice expanding just to make sure our polynomial work is good. So degree 2 means there's 2 of them, right? So we're picturing, right? So this is what I'm expanding out. Right? So you only can do 2 at a time. So h of x equals, so x times x is x squared. I'm going to put the 2 middle terms together. We're 30-1 now. We should be able to do this in one step. Do you guys agree that I'm going to get a 2x plus a 2x, which is going to give me a 4x in the middle, so instead of doing 2 steps there. And then my last terms are 2 times 2, which is a 4. So that's what I would get if I expanded the first 2, because you only, like I said, when you're multiplying, you can only multiply 2 things at once. Now, I have to go again. So here I'm going to write all the terms out because I can't simplify all the pieces because it's a 3-termed polynomial times a binomial. So away we go. So it's going to be really long. How many terms am I going to have when I'm done expanding this before I simplify? 3 times 2 is 6. So I'm going to have 6 terms when I expand this. Some will simplify, but we'll do that after. All right, away we go. So x squared times 3x is, or 3x cubed. X squared times minus 4 is minus 4x squared. So I'm done with that one. Now take in the 4x. So 4x times 3x is 12x squared. 4x times minus 4 is a minus 16x. So I'm done with the 4x. Now I take in the 4. So 4 times 3x is 12x, and then 4 times negative 4 is minus 16. And from there I can collect like terms. So our h function is 3x cubed, no like terms for that one. And I have a minus 4 plus 12, those are both x squared terms, so that will give me a plus 8x squared. And then my linear terms go together. So I have a minus 16x and a plus 12x, bless you, which will give you a minus 4. And our last little guy here is minus 16. So the substituting of the functions into multiply, easy peasy. It's just this one, I would say polynomials are the worst to expand and simplify. Most of the other ones won't have simplifying. Because can you guys visualize if I take a radical, right, function and times it by a quadratic function, you can't put them together. So you literally, your first line, you'd be done. Okay, here there is some work I can do to put them together, so that's what it would look like. All right. So, and then the last thing it asked for was state the domain and range of h of x. So my domain, did we get a function that we're used to, guys? Are we used to that type of function? What is that? That is a cubic. Okay. So if you don't remember what a cubic looks like, then you would put it on your calculator to figure out what your domain and range are. But I'm hoping you guys know from the polynomials unit. Do you guys remember that a cubic, right, ends in both directions, right? So this one has a positive leading coefficient. So it goes, the one end's going to be in quadrant 1, and the other end is going to be in quadrant 3. Okay. But again, if you forget, you would put this on your calculator, and you see that it goes forever left, and it goes forever right. There's no restrictions on x, right? Any x real number can go into the function. So then, you know there's no restrictions on x. Where's your booklet? Yeah, still get it out. Just confirm. You might want to scratch little notes around it if you hear something. And then, and again, this is coming from you picturing this. That's what you would picture, or put it on your calculator, and you get something that looks like that. That's why I know the domain is all real numbers, because it's a polynomial function. There's no restrictions for x. And range, there's no restrictions for y. It goes forever up and it goes forever down. So my range is the same, except it's my y's. Just a quick reminder, guys. If this was a degree 4, would we for sure have to use our calculator? Yes, if it was a degree 4, you couldn't do this paper pencil just using your head. If it was a degree 4, you know that a degree 4 or a degree 6 or a degree 2 has a bottom or a top. So if it was a degree 2 or a 4 or a 6, you'd have to go to your calculator and calculate the bottom, right? You'd have to go min, or if it was the bottom, it would be a min, right? So you'd have to go calculate minimum to figure out where the bottom was, and you'd say everything greater than or equal to that. If the leading coefficient was negative, then there would have been a top. You can't calculate that without your calculator, okay? Algebraically, if it's degree 4, 6, 8, max and mins are done in your calculator. Okay? Till you hit calculus, then you can do them algebraically, which is a lot of fun, okay? But 30-1 don't have those skills yet. So max and mins are done in your calculator if it's higher than a degree 4, or 4 included. All right. And even degree 2s, you guys know how to do those algebraically from 20-1, but why do them algebraically? Just use your calculator. All right. So are we good, guys? So just the idea, multiplying functions together. So the your turn I'm still going to do with you guys, okay? Just because I want to do the sketch without the calculator first and then confirm it with the calculator. So here, two different functions. So now I have a quadratic function, okay? So my f function is 0.5 x squared, and my g function is square root x, so a radical function. So determine h of x if we're taking our f function and timesing it by our g function. So let's do that first. So equals, so my f function, put it in. So this gets substituted in here. And this gets substituted in there. That's all you're doing. So we have 0.5 x squared and then times root x. Before we do anything else, guys, does that new function have restrictions? Yes. What can we not take the square root of? Negative numbers. So therefore, before you even start, we know that x has to be greater than or equal to what? 0, exactly. Because whatever the expression is underneath the radical sign, you know has to be greater than or equal to 0. So remember in our transformations unit when I had stuff like this? You guys remember doing stuff like that? And you had to say x had to be greater than or equal to 1. It's the same idea of what we've done in the past. Except we're getting kind of new, different functions by combining functions through multiplication. Right. So that is our new function, and as I was saying, guys, we're not doing anything with that. You're not simplifying, you're not taking anything like that x squared, we're not putting it under the square root. That's done. There's no putting more terms together like we had to do with the polynomial one. So that is finished, boom, done. Now given the graphs of f of x, so y equals half x squared is the red graph, okay? Y equals root x is the blue graph, so those were already graphed there for you. Now it's saying sketch the graph of h of x. So guys, I know we could put that onto the calculator, okay, and graph it using our calculator. That's the easy way to do it, which I would encourage you, if that happened on your quiz, definitely use your calculator. But do you think on your quizzes or unit tests that I just might give you a graph with no equations and ask you to sketch the product graph? Yes. Just like I did last class, guys, where I said, here's two graphs, do the sum graph or the difference graph, okay? And it's not hard. It's just like we did last time. Sum graphs, what did we do with the outputs to get our new number? We added them. Remember our difference graphs? We would take the outputs of the original graphs and subtract them. Guess what? So with our product graphs, we just take the outputs and multiply them. Right? So that process, right, is very similar to what we've just done. But with this one, you guys have to realize, where do I start multiplying outputs? Where do I have to start multiplying outputs? Where's the first point going to be? At 0. Because This graph right here starts at 0, so nothing can exist over here because there's no 2 outputs on that side. So with this one, whoopsie, you do have to make the connection that the first ordered pair of our product graph is going to start where x equals 0, because that's where both graphs have outputs. Okay. So let's go ahead. So I'm going to find h at 0, so equals. So I'm going to take my f graph and times it by my g graph. So technically, guys, it doesn't matter which number I write first and which number I write second. No, just because product, it doesn't matter order. So, but just so I'm following the order, this is my f graph, so I'll do that number first, even though it doesn't matter because it is a product. So I'm highlighting it so I always go back to that one. Okay. All right, so at 0, so my highlighted graph at 0, what's the output at 0? It is also what? 0, right? So my highlighted graph has a 0, 0 point. Now on my blue graph, what's the output at 0? It's still 0. So 0 times 0 is 0. So one ordered pair is going to be 0, 0. Now h at 1. Okay, so at 1. So I'm here at 1. I'll move that up a tiny bit. So at 1, my highlighted graph is about what? So the red graph, or the quadratic graph. Where's the output at 1, approximately? 0.5. Do you guys see it's 0.5? So it doesn't all have to be nice numbers. Okay, we'll approximate. So my quadratic graph at 1 is about 0.5. So that would be my output at 1 for my quadratic graph. Now, my radical graph at 1 is actually, what's my output on the radical graph? 1. So another ordered pair at 1 comma 0.5. That's easy to sketch that. Okay. Now h at 2. So at 2, my highlighted graph is, so my quadratic graph at 2 is 2. Do you guys agree? Do you guys all see that? Yeah. And then my radical graph is what? About 1.5. Right, so then 1.5. So then that's going to be 2 comma 3. Makes sense, guys, what I'm doing? And again, you don't have to go 0. The point you for sure have to start is at 0, right? That's the one you have to for sure sketch, okay? Because that's where the product graph starts. But you could skip some. You don't have to go 0, 1, 2, 3, 4. I started that way just to see what's happening at the beginning. So let's be crazy and skip one. Let's go to 4 now. All right, so at 4, this graph is 8. Right, so my quadratic graph is 8. And then the blue graph at 4 is 2. So then I have 4 comma 16. That's probably enough. Let's sketch those points and see if that's enough. Or do you guys want to do one more? Let's do one more. So let's do 6. So at 6, my highlighted graph is 18. I'm just double checking. Is 18. And my blue graph at 6 is 2.5-ish. So that would be, what, 45? Let's double check. So 18 times 2.5. Yep, I'm not being crazy. So that went off my graph, so I can't even use that point, which is fine. So now we can sketch. So 0, 0. Just going to get rid of the highlighted so you can see my points. So 0, 0, 1, 0.5, 2 is 3, 4 is 16, and then 8, sorry, that should have been 645. Sorry, guys. Write them down, right? But 645 is off the grid, so I can't sketch that one. So that's enough. So we have our nice little curve, and up we go. And I know you're probably thinking, Calvert, why would we do that when we have the function in front of us? Because you're not always going to have your function in front of us. It's fair for me just to give you this and say, this is your F graph, right? This is your G graph. Find your H, or sketch your H of X graph given this. So that would be fair for me to do. So you will not be writing the equations. That's way too complicated. You should just be able to take all your ordered pair outputs, multiply them, and then get your product graph. So then with that, we can check. So clear 0.5 x squared square root x, oops, and then get rid of that graph. And again, if we change the window to exactly that, it would stretch out a tiny bit. But you can see we got the perfect shape, right? Boom, bang, did it perfectly. And then lastly, it does say domain and range. So your domain and range is, we already knew the domain because we had our product graph, restrictions on x. We know that x has to be everything greater than or equal to 0. And we can see that from our graph as well. We can see from the green graph that it starts at 0 and goes forever right. Okay? And our range starts at 0 vertically and goes forever up. And we're done. So that is enough for now. So we're breaking it up so you guys don't have to listen to me for so long. So what I did was the textbook questions I broke up. So these are the questions from the textbook. Please try them. Do a couple products, okay? And then in 10:15, we will do the division. Because the division one, same idea, just a little bit more to worry about when you're doing division graphs. But we'll talk about that in a little bit.